Good afternoon, everyone. Welcome to Wednesday afternoon's tutorial. We'll talk about that question in a second. That's a very, very good question. And the answer to that might surprise you. Clickbait follow. Right. So today we're going to continue with our discussion on random access files. And there's a few things that you might have considered by now. On Thursday and on Monday, we've discussed random access files, and we kind of duplicated what we did on Thursday just to make sure that everybody is kind of on board of where we are. Now, today we're going to introduce a new concept to that. We're going to introduce hashing. Now, is there anyone here that is aware of what hashing is? Either hashing itself, a hash value, or a hash function. Hash cookies are good. It's only legal for personal consumption, but sharing is caring. And I am not promoting drug use. Drugs are bad. Okay? All right. So, getting on to today. Today we'll be discussing what is hashing. We'll discuss how to hash, and we'll discuss when to hash. There's a time and a place for everything. So, writing records to a file. So what you're used to is the fact that we want to save a unique identifier and use that we want to save a record to a file using a unique identifier so that we can find that specific record. So in the example we've been using a student. We have the student number, we had a name, and we had a average. Those were the three things we're saving, and we used the student number, the ID, the student ID, to identify the location of where we want to store the information. Now, if you consider that student number is an integer and that you're saving specific packets, let's consider you start with packet 0 or record block 0 and going all the way to record block whatever our maximum allocation is, which in our example will be 217099999. Now, you can tell me what's the issue here. So we are identifying. Sorry, let me just find my cursor. We are identifying these three that we want to save. Now, who can tell me what's an issue here? When we save, we take the identifier, we multiply that by the data block. You are all comfortable with that, right? Oh, you guys are quiet. Okay, so let me rephrase that. To save to a file, when you seek open bracket the student ID multiplied by the bytes we have. And I think if I remember correctly, in this example, we had 42 bytes that we were saving. So you took the student number, multiplied by the number of bytes, and that would give you your beginning location. That's where you'll begin to save the information. Now, you can tell me what's the issue here. It will exceed the int size limit, won't it? Not in this case. So this case, it won't exceed the integer size limitation, but there is a different reason why it is a problem. And you can think of that reason. And look at the screen. Really consider what's on the screen. Each one of these are represents a specific record block. So you've got block 0, block 1, block 2. And then when we look at a student number, the first student number we are looking at is essentially 217012345, or in other words, if you have to break it down into a numerical value, 217,012,345. So the issue is not the collisions. We're still going to discuss collisions later on, but what is the issue here? Think about a student number itself. A student number always has 4 digits that indicate the year, 5 digits indicating which number you were in that year of registration. What does that mean? Where is this file going to start, and how much empty space is going to be before that file? Because if you're only going to start on record block in the millions, let's say you'll start at 200 million. You're going to start with record block 200 million. It means you've got 200 million empty record blocks before that, because 0 to 200 million is never associated with any of the items. That is correct. It will be empty, which means, where's my cursor? Which means we have a lot of space that we're wasting. So we need to find a way to compensate for that. So let's assume that we have 18 blocks available to us. So also random access files are created with a fixed number of record blocks. In our example, let's say we only have 18 blocks. Now, until now, we haven't shown you how to actually set the size of the file before using the file. We've only shown you how to actually write things to the file itself. But let's assume we only have 18 blocks available. And in the code, we'll assume we only have the 18 blocks available. How do we make sure that only these 18 blocks are going to be used? Now, in our situation is the fact that we want to convert that number, that student number, into a numerical representation of the position, so that we know where we want to store it. So the solution to this is hashes. No, not the hash that you peg in both sense of the word, I guess. It's a hash value. Mapping a numerical value or just a value. It can be any value. It can be a numerical value, can be a binary value, can be any form of value. So you take a value of any size, you put it through a hash function, and you return a value of a fixed size. And in our case, it's a value of a fixed size that will be limited to 18 spots, giving us a position between 0 and 10, or 0 and 17. So we want to make sure it fits into one of those 17. So if we take the student number 217012345, put it through our hash function, we will get a value out that will tell us that this specific student correlates to the position 9. Now, one thing you should note, a hash function in a general term should return a unique value. I'm saying should, not always. It depends on what type of a hash function you're using as well. In this case, we've got 17 blocks available. Our hash function is going to return a value between 0 and 17, which means we will have a situation of a collision somewhere down the line. But we're not going to discuss how to work with that today. That is what we'll be discussing tomorrow. So it's a key pair relationship. Not really a key pair relationship. If you're talking about a key value or a key pair relationship, that is associated with a different type of structure. That's generally associated either with a linked list or with a graph or a map. What we're referring to here is simply just a hash value. So your key gets converted into a hash value, which is where the information is going to be stored. So the key will just be a position. Now, if you look at how a map itself works, your position is identified based on a numerical representation inside. But in our case, that's not the data structure we're using. Yes, it is a key that will give you the position, but it's not referred to as a key pair relationship here. All right, we count out 0. 0 does count, but 18 blocks means we've got 0 to 17. The data file begins with byte 0. All right. We'll be covering salting as well in IFM. We'll be discussing some of the more additional hash functions like collisioning and chaining and bucketing next week. So salting is a slightly different term. It's more of encryption, but we'll see how far we get. We'll discuss the additional concepts next week when we have time for it. But there is a few things we have to get through first. All right. Then there's another student number which can get converted, and so forth and so forth. So the idea here is this hash function will give you a value that guarantees that you will have a unique output between 0 and 17. Now, please keep in mind, I say unique. If you look at how many student numbers there are, and with the hash function we're using, it's guaranteed there's going to be a collision, but that's not something we're going to consider right now. We're purely going to look at the hash function itself. Collisions are handled separately. So this does unfortunately require maths. So how do you actually do this? How does this hash function work? So when you're working with a hash function, there's three things you need to know. And we'll be working with a prime number division remainder hash algorithm. It's a fairly known algorithm. And the reason why we use a prime number are for two simple facts, and we'll discuss it as we go along. So the first thing you need to know is you have three things to keep in mind. You've got N, P, and H. You need to identify N. N is the number of records that exist in the file. So that is the size limitation of your file. It will be between 0 and whatever the file or the number of records are that you're going to be expecting. So N is your data set size, how many record items you're expecting. And we're talking about records here, so it's the complete information inside the record makes up one record. So the student number, the surname, and the average makes up one record. We count how many of those records we are expecting. Then we identify P. P is the largest prime number less than N or equal to N. Nothing larger than N though. Now, we are trying to obtain H. H is basically the remainder once you take the record's key and divide it by P. Now, you can identify what you know of a prime number. I'm assuming you guys all still remember the rules of a prime number. Why are we dividing by a prime number? What's one of the conditions of a prime number? And I'm specifically looking at the remainder of a prime number. Remainder is itself and 1. Only two factors. It is not divisible by any other number. It is divisible by 1 and itself. That is the specific term we're looking for. Now, the reason for this is when you divide by the prime number, or you mod, essentially, you're interested in the remainder. Your remainder is unique to the value in terms of your integer return. So the only number that will correctly divide the prime is 1 and itself. Everything else will give you a return value of a unique identification. So if you take 19, for instance, or in our case, we take 17, you can see that if you take 17 and you divide a value by 17, you'll always get a value returned between 0 and 17. Well, 0 and 16 essentially, but the idea here is that you get a unique value back, or you're supposed to be getting a unique value back. Now, there are some situations with collisions, but like I said, collisions will be handled separately. We're only in the function that will guarantee us a return between our 0 and our prime number. Now keep in mind, we said there are 18 spots available. We are now using a prime number of 17, which means the return will be between 0 and 17. Well, 0 and 16, because if you give it 16, the remainder is 16. Now, how do you use this inside your code? So this code that you're used to currently. Keep in mind, we're still not setting the size of the file. We're just identifying the location of where to save this. So right now we've got student.id multiplied by 42, which represents the location. Now, in order to make sure that that location falls between 0 and 17, we use the hash function there. So we provide it with the number, the value that we want to hash, and that function returns a hash value, which represents the position of where we want to store our item. Math fun. Oh, just listing all the prime numbers, but they should know most of the decent prime numbers, I guess. Now, how does this work essentially? So let's go to, you'll be coding that hash function itself. Because remember, you're setting the function itself, you're setting the prime number that you're using to divide by, so you have to create that yourself. So that hash function, this specific hash function, is one that you're going to create. There are a few built-in hash functions, but we're not going to be using them. We were going to include 17 as the prime number if 17 at 17 spaces in the file. Well, if you look at the actual function, if you take here's that function now. If you take 18 spots, as you said, there's 18 spots available. The closest prime number to 18 is 17. So with 17, if you divide something by 17, it's going to give you a return. The remainder is going to be given you, sorry, the remainder will be a value between 0 and 16, because if you give it 17, 17 will just return a 0. And then anything going upwards will still give you a return. So the idea here is that it will fall in one of these spots. Now, looking at that just on a screen like this doesn't always explain what's going on. So let's actually look at this hash function. I'm saying function. Let's look at it in a Excel representation so that you can kind of see what's going on. I just want to introduce you to the hash itself. So let's give it about, if you use the prime number method, is it not predictable based on the amount of records? And if you don't store the number of records, how could you read the data? Okay, I think I'm reading your question correctly here. Okay, so let's split it up. If we use the prime number method, is it not predictable based on the amount of records? How do you mean predictable based on the amount of records? Remember, we're not trying to keep something secret. We're just trying to get a position itself. It's not like your SHA-2 hash functions where you have a unique value representation that obfuscates the original value of that whatever you're giving into the hash function. The idea here is that your return will be the location of where you want to store the information. And if you're storing the information, you're going to provide it the key, which in this case is the student number. You're going to hash the student number, and that will give you the location of where you're going to retrieve the information from. In our case, we're going to be using integers, but it's not just integers. If you look at a hash function itself, generally a hash function returns an alphanumerical value. It's not just a string integer representation. In this specific hash function, because we want a numerical return and because we have a student number, we're going to assume that our things will just be with integers, but it's not just integers. It just depends on the function you're using itself. So if you have 6 records, you use the closest value to your prime or equal as the closest prime to your value or equal to your value and not more. So the idea is to get a return, a return. Now, if there is a collision, you'll use something else in order to find that specific information. So you'll use something like chaining or bucketing to just kind of shift it to a different spot, but so that you know where you're shifting it to. But that is something we'll discuss next week when we discuss collisions with hashes themselves. Now, just to give you a very, very simple example of what a hash function or what our input and output will represent. If you consider the values that we're testing, let's just go to those three values. So the 21, 70, 1, 2, 3, 4, 5. Okay, 21, 70, 1, 2, 3, 4, 5. And we have our function itself. So we're going to mod. We've got our value we're modding and our divisor, which in the example we said is 17. And that will give us a return. Now, if you keep on taking this down, let's just see if we get this not playing nice today. Yeah. So we've got a list of students, and let's take it all the way down to 17. Let's take our function down as well. You'll see that we get a return. But now, you'll see at some point we do get repetitions. There are values that, based on the division, will give you a collision. So let's just go take this down. All of these are repeating the same value. Excel is not being nice today. So you can very clearly see already with just these values we want to test out that it becomes difficult. But I'll give you an idea of what's going on. So you already have repetitions, but you can see it goes all the way up to a 16. No issues there. But the issue comes from the fact that with this repetition, there's collisions. Something to be handled next week. But keep in mind, we're only expecting 18 values, nothing more than 18 values. So generally speaking, within the associated data design, we shouldn't be getting a collision because the expected results will only be 18. Now, if we start looking at an increased data set, let's say we're expecting 165 or 165 values, then you want to use a prime number that is close to 165. So in our case, that would be 151, if I'm not mistaken. Did anyone open up that link yet? Let's just see. Yeah, 151. So if we go up to 156, being that the next prime is going to be 157 and the prime before that is 155, then we will use 155 as the prime number, if that is the number of records we're expecting. So 151, take that function all the way down, and you'll probably see that there are no duplicates within this range. So within a range of values given, you shouldn't really see duplicates. But then again, it's not guaranteed specifically because of the algorithm we're using. It's not unique. Let me just swap back to. So there was a question there. How do we read hashed data back into our program? Student number hashed stored hash function student number. No. So once you've converted, a hash function is only one way. You can convert it in one way and not back. Because remember, it is a hash function. It's only going to give you a part of the data set or a fixed value return, which in this case, our fixed value guarantees us a value return between the 0 and the prime that was chosen. Now, a hash function, a hash value, never gets returned back. So the idea of a hash function here is to find the location we're going to store the information. If you want to take that specific student number out, you need to search for that specific student number, which means, let's say we're looking for your results. You will give the program your student number. The program will hash your student number, find the location of where it can find your details, and read that information. So it's not a case of where you read the entire file and then try and convert the hash back. It's simply just the location. It's not a value that's ever noted in the file itself. The file will still be your student number and still be your surname and still be your average. So if you go back to these slides, just to take you back to that slide, the idea here is that you will have that value will now be between 1 and 17. Now, to make things a bit simpler, do we still have that program from last night? Let me check if I still have it. Let's just show you the actual values. Now, ignore the front end. We're just going to look at the code. You don't need to memorize the list of prime numbers. I mean, there's a link for you. You can use that. So let's just go to where we create this file. So let's just call this file, this is a lecture, and we'll call this file hash. The remainder, that doesn't really matter that much. Now, if we go to where we create this file, let me just go to where we create this file. Create file, just give me a second. Over here. So over here, we're creating this file essentially. So we've got our file stream, we've got our binary writer, and here we're writing information. Now, this is just representing blank information that we're writing. So I'm going to comment this out, and then I'm going to show you. The data wastage. Come on, let's just do it on the next line. I'm using the wrong language here. Never mind. Just wind it up. Right. So, if I seek, we give it a value that we're aware of. So let's give it that 27, 1, 2, 3, 4, 5. We multiply that by our record size. Our record size in this case is still the same. So our record size is 42, if I remember correctly. No, it's 56. Oh, but this is the data set that Mr. Koch was using. Our record size for our student was 1 integer. So you're looking at 4 bytes, 1 double, 8 bytes, and 1 15 character length. So we're looking at 30 there. So you've got 42. Oh, it's right there. One moment. So our record size is 42. Then we have the origin. So that would be then the seek origin, where it's beginning, which is just essentially the beginning of the file. The seek origin.begin, which says you're going to begin from the beginning. Now, in this case, we have our blank information that we want to write. So we're going to be writing that blank information for our student, which is going to be, just going to do this by hand so that you can see what the file structure will be once we have this specific output. So we're going to have the value 170123455. Where did I write for? Oh, thank you. We've got the student number. We're going to write the surname. Surname can be anything, so let's just go anything, but limited to 15 characters. Remember that, because of the character limitation that we set on the string, which is 15, we need to make sure that we give it a string that is 15. and then write an average, which in this case was a double, so we'll say this is just 12.12. Now, if you save this information, what will this look like inside our, let's just close that. What will this look like inside our file? Any ideas? Let's just see what the issue here is. That's going to return a value that's a bit long. Let's see. Don't want to convert this. Let's just get this down. Okay, that will suffice. So, file location, we cut it down by one more, but file location is determined by the value inside our data set. That's our key, multiplied by our data maximum data allocation, which is 42 bytes, which is the maximum expected data size of our input. Keep that in mind, because that determines the blocks. So every 42 bytes in this file represents a block. Now, if we save that, run that essentially, just creating this file, let's just see what the file itself is going to look like. So in this case, I just want to show you what happens if you use that student number, how many empty records you essentially have. Okay, it's now writing. And it's going to probably take a while to write. Okay. I believe it has now finished. Yeah, it should be finished. So let's open up that file so that you can see what the file would look like. So we called it lecture hash. Open that up. It's just going to take a while to read. So the first thing you'll note is look at the size of this file. So essentially, it had to create all the empty space before where our location of that specific item is itself. Now it's just trying to load up all of that information, which will take a while. But can you see the fact that because we're saving at the, what's this? This would be 21,701,234 position, fourth position. It has to create all of those empty blocks beforehand. And it's still going. So that's going to take a while, because now it needs to read up until that point. And did it crash? Is it opening? I think it actually crashed. No, it's there. And it's still trying to read everything. So can you see that it is already an issue trying to fill all of those spots? Where if we just simply converted this, and let's just do a simple hash function. Let's say we're expecting hash. We have a value as integer. We'll have an integer return, and all we do is we return the value mod, what was it, 17. All we do there. Then in our function itself, what we'll do here is we will hash our number. Making sure we hash the correct number. We'll hash that specific number, get a return, which will be a value between 0 and 17, and then write that to a file. Let's see. Okay, there we go. So, as you can see, and this is going to take a while, everything before the value that we've entered are all empty blocks until And it crashed on me again. Until the very last spot where we wrote our information. Now, I would like to show it, but I don't think it's going to get me all the way down there. So you can see it takes a lot of space. So let's just close this because this is going to take a while. Close the program. Let's just go to that file. Let's just delete that file. And let's just recreate this based on the hash value that we got. We write that. You run that, just recreate that file, which in this case is just putting that inside the file. We go to the file location. We have our function. We see it's 1 kilobyte, far less than the other one, and you'll see our information. So far less information than the previous set because of the hash function, because it is now limiting the amount of space we're going to be using to a few blocks instead of thousands and millions of blocks. Now, one thing to note, if you're working with thousands of positions, you're not going to be working with files like these anymore. You'll be working with a database. Let me just get to those questions. Right. What were those questions? What's the difference between the position and the record position? Okay, so the record position is where it is in this specific file. So you've got data blocks here. So let's just execute the program here for those that weren't part of the lecture last night. Right. So what's happening here is we've got a number of records that were predefined. We're writing those records to the file, and we're just writing blank information. Now, I'm just going to multiply our record number, which will be 1 to, I think it was 30, 1 to 30. I'm going to multiply that by 2. So I'm basically doubling the record sizes, which means there will be empty records in between. But I just want to show you that when you write blank information, all of that is just blank information. The file itself will have those blank information inside. So you can see you've got your data block. That data block represents one record, whereas this empty space is essentially unallocated space itself. And because the program doesn't write that empty space, because it's unallocated, it just leaves it empty. But until the block where you write information, if it goes to that position, everything before that position will be written as null. So in this case, I'm skipping a record every single time, or I'm skipping a position. So you've got your data block being written, and that is essentially the information that is just blank, and then empty space, like there's nothing there at all. And then it goes to the next block. So these are positions. This is the starting point of the next record block. So that is read as the file position inside, or the record position. I say file position and record position. I'm using the terms as similar. I'm using them for the same thing. So just get to the last question there. So what would be the practical application for this? What would be the practical application for this be? Storing medium amounts of data in storage instead of RAM. Now keep in mind, anything that is active inside a program is going to be inside RAM in any case. If you've got a program open, that information is stored in RAM. It just gets converted from or transferred from your RAM to your storage once you're done. So while I have the file stream, let's just close this. While I'm running this program and I have this file stream open, this essentially is that file being in RAM. So the entirety of that file in RAM is this specific line. This, when you close it, is when it gets removed from the active program. So it gets moved from your RAM or your memory into storage. So while the program is active, it's considered to be in RAM if this is open, because that file stream is your temporary file. When you're writing when you're reading, you're loading it into RAM so that the active application can use it. Whereas if you close it or flush and then close it, then it gets stored into your secondary storage, which is your memory. Which is your hard drive or your SSD or your NVMe or whatever you're using. Now, when you work with information like this, depending on what you're using, it's very quick to find information. So consider you're using a sequential file, and you've got 100,000 records in this sequential file. In order for you to find information, you have to go through the entire file stream, one by one, to find what you're looking for. Whereas with a random access file, all you have to do is open up the file and go to that specific location. So yes, the entire file is still in memory, but you can very quickly search this because you know exactly where to go in that file. It's not the case that you have to go one by one through all of these data sets or records in order to find what you're looking for. Does that help your, does that answer your question? Now, when we're moving over to databases, they are handled very differently because you're looking for very specific information. So you're telling the program, I want this information, and it goes and it pulls out the information for you. So when you're working with a database, the database doesn't remain an active memory or the entire database. It only goes to the program and tells the program, I want this specific block of information, go and find it for me. Whereas with a sequential file, you have to load everything into memory, and then you have to load every single item one by one so that you can go through them one by one. Whereas with random access file, you've got a key, which is your student number, and then you can go and retrieve the information you specifically want. Are these types of files queryable? So a random access file is a lot closer to a queryable file. You can essentially, with some VB magic, set up a query that can find information from that block for you. Yes. Sequential file, not, because a sequential file, you still have to load every single item into your system in order to find what you're looking for. Now, keep in mind, when you're looking at a queryable file, is a queryable file, you're referring to something that you can query the data set inside the file itself. Whereas with a random access file, you need to know the position of the file you're looking for or the item you're looking for. So you need to know what the key is. If you don't have the key, it's the same as a sequential file where you have to just go one by one to find what you're looking for. So you can do the same thing with a random access file that you can do with a sequential file. But if you have the student number or if you have the key, you can jump to the position that you want and just read that position. So it's searchable. It gets closer to a queryable situation, but it's not necessarily queryable. You'll have to do some VB magic to make it queryable. But then you're still loading it into active memory, which is still a waste in terms of other data structures that you can use to query it. All right. But that's going beyond the scope of what is required for random access and sequential files here. You'll learn about queryable files in 2A. Are we multiplying 17 times 42? So the 42 is your data packet set. So let's look at our Excel, which is once again a very good way of looking at this. Let's just start from the top. Consider the fact that you have a block. This will be a block of information. So you're looking at your student number. So 1, 2, 3, 4, 5. I think it was control. Let's control. Just give me the Excel magic for. Okay, shift. Never mind. You've got your surname, and you've got your average. Let's just put this in the first block. So that is your data size, your data set. So this specific block that contains the student number, the surname, and the average represents 42 bytes. That's a maximum of 42 bytes. What our file is doing is essentially creating these blocks. It might be empty blocks, but it's creating these blocks. When we're looking for a specific student, what it is doing, it takes that student number, gets a value between 0 and 17, which then represents which block that file, that information will be in. So 42 is just the block spot, because each one of these are 42 bytes. So this will be block 0. It starts at byte 0, ends at byte 41. Block 1 will start at byte 42 and end at byte 83. So that's why we're multiplying by the 42. So it's the actual byte where we're going to start reading information from. The 17 is the position. So in that case, we'll start at block 17, but the multiplying is in order to tell us what the byte value is of block 17. So block 17 would be byte, let's say 17 times 42, will be byte 714. So it will open up the file, go to byte 714 in the file, and start reading from that byte. All right. So that's why in programming, or in the examples, I'm still using, in the lecture slides, I'm using the actual value. But it's a good thing if you set the data record as a variable for yourself, because then you can just keep on using that record size. You can keep on giving yourself a reference to say, this is the record size. So let's see. Can we get the byte value of a structure using a function, len or size of or something? Well, why do you need to get the byte size of a value? You should know it by now. Because you know an integer is represented by 4 bytes. A double is represented by 8 bytes. A character is represented by 2 bytes because the location is using a Unicode. So every character that you have 2 bytes. But keep in mind, we're not interested in how much bytes is actively being used, because you can get that. There's a function for that, and that is quite easy to get. What you're interested in is the maximum allowed allocation of the record. Just keep in mind, you're allocating blocks to your random access file. So you need to know exactly what the block sizes are going to be. So you can't have a variable length size in that. Because if you have a variable length size in, let's say, the string, let's say you limit it to 15 strings, and then you exceed 15 strings, when you allocate the block sizes and it's based on 15 characters, once you go to the next block, your first block will override that information unless you're writing them one by one. But what will happen is, let's say you write block 1, block 2, you modify block 1, and then you increase the string inside that to, say, 17 characters, which now exceeds the actual block size of what you're storing. So that block is not 42 bytes anymore. That block is now 4 bytes more. So you're looking at 46 bytes, which means it's going to it's going to modify whatever you had in the starting of block 2. So you're overriding information in your second block, which is something you don't want with random access files. So you need to make sure that you stick to the size that you set for your record structures, and that maximum size is how you determine the record blocks that you're creating. Otherwise, you'll just be overriding them. Sequential files, it doesn't matter what the size is, because it just saves it and sets an end of object parameter. And a random access file does actually set an end of object parameter, but you can still override that because how you are storing information. All right. Does the length of the integer matter when considering the bytes taken? Let's say that the integer value we are trying to store has 7 digits. Will it still consume 4 bytes of storage? Yes. So integer is that actual data type. An integer is limited to a certain number of character representations, if I can say that much. So there is a maximum string length, maximum character length inside an integer. So if it exceeds an integer, you go into a long, and then if it exceeds a long, then, well, it's generally not a mathematically representative value, then it starts going into a string, depending on what that information represents. Now, in our case, A student number, if you're looking at how information is actually being stored, a student number will not be an integer. A student number will actually be a string. For our example, and to make hash functions easy for you right now, we just use string as an example. I mean, integer as an example. But once again, those are things, when we're talking about keys, you'll learn more about keys in your second year when we actually go into detail about what is required, how do you look at them, what data types they're supposed to be, and all of those things. All right, this recording is going slightly over time now, so I'm going to stop the recording here. If you have any questions, please do ask them. I'll still answer them. But all you have to take away from today is the basic hash function. It's the fact that you give it a value, you do some mathematics with it, and it returns a hash value for you. That hash value is the position of where information is being stored. Now, more on that will come next week. All right. So if you guys have any more questions, you can ask it in the chat, those that are here live, and those that are watching the recording. If you have any questions, please just drop them in Discord. Please note, we do sometimes, because of how the messages are being displayed, skip 1 or 2 questions. If we skipped your question by accident, please just repost it so it's at the bottom so that we can see it. We try and answer all the questions, and as soon as possible. Other than that, I'll see you guys in the next recording or in the next live session.